Okay.
Good. So I'm happy to introduce today Jong Chul Ye from KAIST in Korea. He did his PhD in 1999 at Purdue, then worked actually for Philips and for GE consecutively before he returned to Korea and made a career there. And since 5 years now, or more than 5 years, he's now endowed chair professor at KAIST. And today he will speak about generative and self-supervised learning approaches for inverse problems. Please go ahead.
Okay, thank you very much for the kind introduction. Let me share my screen. Okay, can you see the screen now?
Yes.
Okay. Yeah, thank you very much. Thanks again for the invitations, and it's really great, my honor to be here at Isaac Newton Institute to give a talk on our researches. Yeah, the title of my talk today is Generative and Self-Supervised Learning Approaches for Inverse Problem without Pair Training Data. Okay, even though the title is a little bit more in general, but however, this talk is mainly based on the following two classes of works which has been conducted from our group. The first one is actually Note to Score, which recently accepted in the news 2021 as a self-supervised learning approaches. And the other is optimal transport-driven cycleGAN approaches, which we have been exploring for the last 2 years. Okay, so as you know that deep learning approaches has been originally mainly used for the diagnosis and image analysis. For example, when in this case images come in, then your network is trained from the images to do the clinical diagnosis, so image analysis like a segmentation or registration and etc. But now, deep neural network has been widely used for the inverse problem approach as well. In this case, neural network input is more like a sensor measurement, and output is generating the images. So here the goal is to generate high quality images from the noise measurement or like a sparse measurement as well. In fact, this kind of approach has been mainly investigated within the framework of the supervised learning approaches. Here, the idea is now we have a cost function for the supervised learning loss. Here, this X itself is actually the ground truth image, and F theta is a neural network parameter with the theta, and Y is a noise measurement or sensor measurement. And the goal is to try to find the neural network parameter theta such that once it is trained, and if we put the measurement Y, then you can actually generate the output using the feed-forward neural network. As you can see, this is the simplest way and the fast method to generate images from the sensor measurement. And also, this CNN, for example, is learning the direct inverse operation. However, the downside of this approach is we need a lot of training data, especially for the pair data on ground truth as well as a measurement to have a supervised learning approaches. Then the question is now, what if we do not have any label data for the training? In fact, this is a very important problem in inverse problem in general, which we encounter quite often in many applications. For example, let's think about the multi-phase cardiac CT imaging. Here, you acquire some of the phase of heart at the high dose and the other phase in the low dose. And you are trying to ask the noise image, remove the noise in the low dose phase using the high dose phase images. However, heart is moving, so because of that, there's no pair data. So supervised learning is not possible. Let's think about the meta-artifact removal in the dental CT application. Now, in order to have a supervised learning, you need to actually have a dental CT image without metallic insert for the same patient. That's basically impossible. Now, let's think about the remote sensing application. Now, some of the remote sensing sensors in the satellite is often corrupted with the device's malfunction. Like you can see this kinds of artifact from the sensors. Now, in order to do the supervised learning approaches, you need to actually have a clean images without any kinds of sensor errors and with the sensor error together. This is not possible. Now, let's think about the blind deconvolution problem in microscopy. Here, the goal is to estimate the underlying unknown images. So because of that, ground truth is unknown, so supervised learning is not possible. In fact, this kind of unsupervised learning approach is quite general in inverse problem in general. This slide is taken from the Jan-LaCruz ICIP 2019 plenary talk. Here we actually compare this machine learning in general as a cake. So here, let's think about the cake. Now the cherry on the cake is like the reinforcement learning, like AlphaGo is like a cherry on the cake. Or supervised learning is like a icing on the cake. However, on the whole body of the granule of the cake itself, granule of the cake itself, and body of the cake itself is like an unsupervised learning problem. In fact, actually, most of the machine learning problem, the majority of the problem should be addressed using the unsupervised learning way. So this unsupervised learning itself is very important in general machine learning approaches. And for the inverse problem, perhaps you may are familiar with the deep image prior. This is a fully unsupervised learning approaches, and even training is not necessary. Now, Y is a measurement, and now H is forward physics, and you are trying to estimate the image using the Q-set neural network parameter with the set type. Okay, this, however, in this case, neural network works as some kind of structural regularization to match the measurement data. So in that case, you need to estimate this setup parameter for the given measurement. So this requires very expensive computation. Furthermore, this is not an inductive learning in the sense that once your neural network is trained, it cannot be used for other measurements. You need to train this one again for the given new measurement. Okay, so the fundamental question we want to address here is feed-forward neural network which can be trained in unsupervised manner. Is it possible? If possible, this gives an instant reconstruction directly, but training can be done in unmatched data, but for inference is very similar to the supervised learning. In fact, there is two kinds of class of works to these approaches. One is a self-supervised learning approaches, like a noise to, for example, noise to noise. I call this one as a noise to X because there are a lot of variations. So here in the noise to noise, input image is one realization of the noise, and target image is another realization of the noise. Now, if we train the neural network using this target noise images, it turns out the authors in this paper, they show that because of the averaging effect, they can actually generate the clean images. Okay, this is the basic idea of the noise to noise, and also this combination is a lot of different realizable noise pairs, and the performance is nearly similar to the supervised line. However, in real practice, having a multiple realization of noise images is not possible. So because of that, people invented a lot of variations. For example, noise to self, in that case, in this kind of exaggerated cartoon images, now target is a masked image, part of the images, as you can see here. And usually mask is very small, but this is exaggerated. And input image is mask image without this one, okay? The goal is to estimate these pixel values using the surrounding images, okay? Now, the author, in this paper, they show that under some constraint, under some image model, they can actually show that if you train in this way, they can actually estimate the clean images, or at least similar to the clean images. This is noise to X. Also, another type of approach is based on the statistical approach using the Stein unsupervised risk estimation, or SURE. In this case, in contrast to the noise to X, now target image is the same noise measurement Y, and Y is a noise image, and this is neural network. Now you're trying to fit in this data, but if you don't have any kinds of penalty at all, then the neural network ends up with the identity mapping. So to avoid those kinds of identity mapping, what they show is they have additional term, regression term, which is coming from the divergence term, which is originated from the SURE estimation, and they minimize this one, and they can estimate the clean images from the noise images. Another class of work is generative model approach. This is taken from the Ian Goodfellow's Twitter. As you can see that from the 2014, when the generative adversarial network GAN first developed, and now we have a much improved version of the work, and this can be actually combined with the inverse problem as well. In fact, there are a lot of variation in the two classes of approaches, like supervised learning approaches, like the noise to noise, noise to voice, noise to self, or noise to same, and etc., and sheer approaches. And generative learning approaches that are like originally from the starting from the GAN, there is an M-bank GAN, cryo-GAN, and cycleGAN, and etc. Now, the goal of this talk is actually try to introduce two types of approaches our group has developed to actually have a unified version of this supervised learning using some noise to score. This is a new algorithm. And also various types of generative machine learning approaches can be explained using the optimized transport to driven cycleGAN approaches. This is a two topic we are going to talk. I'm going to talk in this lecture. Okay, now let's start with the first topic, noise to score, which is recently accepted in the NeurIPS. Here, in order to understand the meaning of the noise to score, we need to actually give us a comparison with the various existing approaches, like the supervised learning approaches or noise to X and sheer approaches. As we mentioned before, supervised learning approach, there is a neural network and the noise measurement Y, and X is a ground truth image. We need to actually have a ground pair data with the noise image and the ground truth images. Noise to X, they don't use a ground truth data. However, they use a different variation of the G1. This is coming to a different operation with the Y's original Y measurement. For example, adding more noises or like maskings and etc. Okay. On the other hand, sure, just use a noise measurement as it is. However, to avoid any kinds of identity mapping, they actually have additional regulation up here. These three types of approach, and especially two approach, looks quite different. So the question is any kind of unified mathematical framework to explain this? In fact, what I found is there is actually a unified framework which can explain the existing approaches of the self-supervised learning approach. For example, here, let's think about the noise to X or sheer approaches. Here, now you're not training phase, you now estimate this neural network and loss function, which is coming from measurement Y or its variations. And once it's trained, then for the given noise measurement Y, and neural network generate spit out the clean images. Okay. However, what I found here in this paper is this approach is not optimal, and this is actually only developed for the specific noise model. It turns out more general approaches, two-step approaches. Now, the first part is based on the neural network. Now, in this neural network, rather than directly estimating the noise clean images, you are now estimating the score function. We'll talk about the score function later a little bit. So we are directly estimating the score function. Once score function is estimated, now there is a very well-developed formula, which is so-called the Tweedie's formula in the statistics. And using here, you can actually have a cross-form expression for the clean images for various noise model, like the Gaussian, Poisson, and etc. Why this is possible? Let's start with the Tweedie's formula. Tweedie's formula is actually classical result in the statistical literatures. Now here, this is working for general exponential family. Now, general exponential family probability distribution can be represented in this way. Y is a noise measurement and eta is a parameter. Now, this is given by the factorized form here. This is a Y-dependent parameters here. And now this is the exponential term here. And eta is a parameter. Now, Ty is so-called the sufficient statistics. Okay. Now, using the base rule, if you actually find the posterior density with respect to this probability distribution, you end up with this expression. Now, this term is exactly the same. Now, this is given Y, and we estimate the eta parameter, probability density function with respect to eta. Now, this expression is the same, and now this doesn't depend on the Y measurement at all. Now, there's an interesting lambda term here, which is given by the rho Py divided by Pzy here. Okay, this is so-called the this is actually the using the base law. We can easily derive it here. Now, interesting happen when you actually calculate the posterior mean. Posterior mean is coming from the maximum value of this distribution. So you need to calculate the derivative with respect to y. Now, y-dependent term is only here. So you end up with this derivative of this term is going to be 0, and it actually ends up with this expression. So derivative with respect to y, and now you have a lambda y term is derivative here, and now you have a 2 term here. Now this term is rho p0, and this term is rho py here, derivative. Okay, this is in fact the score function. Now using this, we can actually have a lot of interesting denoising formula. Let's think about the simplistic one using the Gaussian noise model. Now y is the noise corrupted, x is the clean image corrupted the Gaussian noise model. Now using the Tweedie's formula, you end up with this closed form solution. You have a y measurement, and this is score function and sigma parameters here. And this is score function for the noise measurement. How we arrive at this? Now we start with the Gaussian distribution here. And from factorization, we end up with the P0 here, like this expression. And eta parameter is now given in this way, x sigma omega. And now this derivative for the given term is given by this. You plug in this one to the original formula here. You end up with this expression. Now the clean image is x tilde. Now you end up with this kind of closed form solution. Now you can do the same thing for the Prof noise model. First noise model is given in this way. You are estimating the x parameter. Now using this kind of factorization, and you end up with this expression. Now the score function is here, but within the exponential function, and this is a multiplicative way of calculating the clean images. You can do the same thing for the gamma noise model, which parameter is given here, and y is a noise measurement, and x is a clean image, and alpha and beta is a parameter. You want a parameter, given parameter. Now using the factorization and sufficient statistic ty here, you can actually use this formula again and put it here, and then there is a score function here. Now your clean image is x hat. So by solving this with respect to x, you end up with this formula here. Now this is score function, this is noise measurement, and beta alpha parameters here. In fact, for all kinds of exponential family distribution, you can actually derive the closed form solution for these clean images. For example, using the different factorization for the Gaussian noise model with the different t values, still arrive at the same equation. And Prof noise model, gamma noise model, as Bernoulli noise, exponential noises, all this one, you can actually have a closed form solution. As long as you know the score function, you can actually have optimized denoising algorithm from as a posterior mean can be obtained using this formula. Okay. So then the remaining question is how to estimate this score function. In fact, this estimation of the score function has been extensively studied in the statistical literature, and lately this has been also investigated in the machine learning literatures quite extensively for the generative model as well. For example, this picture is taken from the Yang Song's GitHub from Stanford, and he actually have a very nice illustration of the meaning of the score function. Now this is a p data. This is probability density function of the data x. Now there's a 2 peak here. If we sample data from this probability distribution, most of the empirical data is around this peak point, as you can see here. Now, score function is, instead of directly estimating p data, we are now estimating the gradient of this one, the vector field of this, to arrive at this peak position. This is a score function. Now, the goal of the score function estimation is you are now having the score model based on the neural network parameter with the theta, and try to approximate this data. So, in fact, the score matching is, however, the score matching function is a little bit difficult problem, impulse problem, because actually, as I mentioned before, this kind of peaky distribution here, most of the data samples around this peak position, but you need to estimate this kinds of vector field in all along the domain. Okay, so this is impulse problem. So to address this problem, we'll talk about later. Then Hibari, Nan, et al., and they actually have a very nice formula of the score matching without any kinds of measurement data at all. But anyway, so this is a very interesting formula. I talk about that one later. But nowadays, most of the things people, but anyway, so for a given data distribution like this kind of vector field estimation on this kind of array is inaccurate. So basic idea of the denoising score function matching algorithm, which is least advanced in this area, is actually coming from the perturb density, which means now if you actually add the noise, Gaussian noise to the images, and in that case, in terms of density function, it's basically convolving the Gaussian kernel as well. So you have a little bit more blurry version of the density function. Because this is blurry function, so you can, if you actually sample from this distribution, you have a more sample, you can actually sample around this area. So using this kinds of a lot of blurrings of this one, density function, you can actually perturb the score. You can estimate this kind of score function more accurately in this region. This is the basic idea of the denoising score matching algorithms. In fact, how can I actually do this one more systematically? In fact, the denoising autoencoder is actually the first approach to provide the systematic approaches to estimate this one using using adding the noises. This appears in Alan and Benjio's in 2014 papers. Now the idea is as follows. Now for the given measurement y, you are adding the noisy version, various value of the noise, Gaussian noises for the image y, for example. And then the goal is try to estimate the original image using the neural network. So that's why it's called the denoising autoencoder. Try to remove this. It turns out, if you actually train in this way, now this f-zeta function estimation denoising autoencoder has actually a very nice Taylor series expansion, which is given in this way. Now this function is given by the y plus this term here. Now this is again score function here, and plus error term, approximation error term here. So this term is going to be smaller as sigma value is going to smaller. So now, if you actually small values, then you end up with this expression here. Now you have very familiar form here. We learned from the Tweedie's formula for the Gaussian noise measurement and the score function. Now, the reason I brought up this one is now, if you see this equation, this minimization problem to estimate the neural network, it's very similar to the noise to X or noise to noiser or noise to Salmon, whatever. We are now adding the mass data or noise data to the measurement and try to estimate, perturb one of the measurement, and try to find the mapping from here. So in that sense, now you can see that this noise to X algorithm is basically the equivalent to the Tweedie's formula for the Gaussian noise cases. Okay, so that means this noise to X may be okay for the Gaussian noise, but for different type of noise model, we need a different kinds of conversions, different types of algorithms. Now, furthermore, this denoising autoencoder, instead of estimating f-zeta directly, you can actually have this kind of transform here, and then convert this one to directly estimate the score function. Because actually this relationship with the score function is now given in this way, f-zeta minus y and sigma is score function. You are interested in directly estimating this score function and put this conversion to the original DA formula. You end up with this expression. Now you are estimating the noise with the different kinds of density functions, variance term, standard deviation here. You are now trying to estimate this one. Once you estimate it, this r-zeta is basically direct estimation of the score function. It turns out, here in this original formulation, to estimate the score function, you need to divide by the sigma term, which is actually unstable when sigma value is small. But however, with this kind of direct estimation, we have a much more stable. And then you can also reduce the approximation error. Okay? Now you can clearly see the score function estimation as well as a noise to X formulation. Now, furthermore, you can actually see the relationship with the score function estimation with the shear algorithm. Now, using the AIDA transform we introduced before here, now putting this one to the shear formulation here, now you end up with this cost function. Now, interestingly enough, that the sigma 4 term can be cancelled. Furthermore, this dimension of y is a constant sum. So if you divide by sigma 4 and divide by 2, this cost function is basically the same as this cost function here. Now, this cost function is very famous cost function, which is so-called implicit score matching cost function, which appears in this paper in 2005. If you actually estimate directly this as a function, you can actually estimate the score function. In fact, from that sense, you can see that shear estimation is nothing but the score function estimation using the implicit score matching algorithm. So now clearly see why that shear works for the denoising problem, because it estimates the score functions. So based on this formula, now you can actually estimate the two steps by combining the Tweedie's formula and the score function estimation. Now, instead directly estimating from here to the noise measurement, we now decouple this one with the score function estimation part using ARDAE. And then once you estimate the score function, depending on the noise model, for the Gaussian, Poisson, gamma noise, we have different kinds of Tweedie formulas, right? Now, but using the same score function. You put in the score function in this different formula, you end up with the clean image. Okay? So this is actually the comparison result, numerical comparison here. Now, this is ground truth image and this is noise image for the Gaussian, Poisson, and gamma distribution here. Now, this is the shear estimation, and Poisson version of shear estimation is the Poisson unbiased risk estimation, pure algorithm. And this is noise to voice and noise to self here, okay? Now, as you can see here, in terms of the PSNF values, as well as the image quality, you can see the structures of this textures here, but the other algorithms, you cannot see these textures. Same thing here, and these textures. And you can see a lot of artifacts, but now you can clearly see this kind of noise to score using the score function estimation. The Tweedie's formula can have a much better in terms of quality as well as the quantitative values. Same thing here. In this Gaussian noise, different Poisson noise and gamma noise, you can clearly see our score noise to score estimation has much improved the PSNF value, even 3 dB improvement here. And also qualitatively, you can clearly see the textures, which was missing in the shear and noise to score algorithm. Now, in these approaches, we can actually make this one as a, here, for example, Gaussian sigma parameter and zeta parameters and alpha beta equal k here. In this case, this parameter is unknown, but you can actually estimate that one directly from the cost function as well. Now, this is an estimated version of the parameters, and this is actually a given version. You can clearly see that the performance degradation is not that many, and it's actually similar to some of the supervised learning approaches as well. And same thing happened in the color images. We have a blind version is similar to the non-blind version, as you can see in this quality images, as well as the quantitative values. In summary of the part 1 for the supervised learning, we actually recently developed the noise to score algorithm. This is actually the unified version of the framework for the existing self-supervised image denoising approaches like noise to X or noise to the serial type of approaches can be actually unified using the score function estimation followed with the Tweedie's form. And as you can see here, noise to score algorithm can be applied to any kinds of exponential fan denoising. Furthermore, even though I didn't emphasize it, now score function estimation can be done using the identical neural network loss function training. For example, and then using the estimated score function, we just use a closed form formula, which is depending on the noise mode. This is different for the pure or shear cases. And in that case, depending on the noise model, they need to develop a new kinds of loss function. For example, Poisson risk unbiased risk estimation loss function. But we don't need that one. we can just using the identical neural network training, and then using the closed form formula, we can actually have a different kinds of denoising for different noise model. Okay. Now, the next part of my talk is actually about the generative approaches based on the optimal transport-driven cycleGAN approaches our group has explored for the last couple of years. I believe most of you are familiar with the optimal transport, but for those who are not familiar with, I'll give you some gentle review of the optimal transport. Here, optimal transport is basically trying to find the transportation map of function from one probability distribution to another probability distribution new here. Now, this is probability space X and Y, and we are now trying to find the transportation map. In fact, this relationship is given by the measure of a push forward operation, T sharp here. And the optimal transportation problem is now trying to find the minimal minimizing the transportation cost under this constraint. In fact, this was originally proposed by the Monge, French mathematician. In the Monge's original optimal transport problem, we have a transportation cost here and X and transportation map here. Now try to find the transportation map T directly under the constant of the push forward operation. However, this problem is a little bit difficult because this constant is nonlinear constant, which is difficult to compute in many complicated distribution model. So this is a little bit more difficult problem. In fact, Kantorowicz relaxed the condition and introduced so-called property optimal transport formulation given in this way. Now here, transportation cost is given here. Now instead of directly minimizing the transportation map, we are now trying to estimate the joint distribution phi under the constraint that its marginal distribution for the joint distribution the same as the marginal distribution nu or mu in this spaces. Okay. Now it turns out that if actually discretize this version of the problem, it turns out this leads to the linear programming problem. In fact, Kantorowicz developed this optimal transportation problem for the to solve the economy problem in Russia is a planned economy at the beginning in the communism. So he tried to actually solve this problem. And because of that, and also because of the development of the linear programming problem, he got the Nobel Prize in economy. Now, another nice thing about the contributive formulation is it's a dual formulation. Now, dual formulation is instead of minimizing with respect to joint distribution, now it's a dual formulation is now minimizing try to find contributive potential with respect to the marginal distribution here. Now this contributive potential and its C transform, which is defined in this way, we are supposed to find the maximum the maximum value of the contributive potential. It turns out this dual formulation is exactly the same as a primary formulation. But what the nice thing about this one is now instead of solving the joint distribution, you are now integrating with respect to marginal distribution, which is much more simple. Furthermore, some of the interesting transportation costs. See, you have a C transform is a very interesting formula, especially if you have a norm constraint. In that case, this is a very simple formula. We'll talk about that later. And based on this kind of formulation, Lei and Na and Sintung Yao from Harvard University, they actually propose understanding. They analyze a generative model in a geometric sense, but the demonstration is like this. Now let's see this kinds of point as a phase images, empirical distribution of sample. Now nu is now probability distribution for the Gaussian noises. Now G zeta is a transportation map, G zeta parameterized like that. Now if you transport this one, the push forward operation gives a measure of mu zeta, which is depending on the zeta parameter, right? Now the goal is try to minimize this transported measure with respect to the empirical measure here. If we minimize this one with respect to this push forward constraint, it turns out this dual formulation leads to the generative model. Now, more specifically, the important thing is not the choice of the statistical distance between this measure and this empirical distribution. For example, now if actually use F divergence here, now it ends up with the GAN or F-GAN formulation. I'm sorry, F-GAN formulation. Now, however, divergence is not a complete measure, it's a matrix. So if actually use all the properties, you can actually use a Bashar-Stein one matrix. In this case, you end up with the W-GAN, Bashar-Stein formulation. Okay. Now, based on this understanding, now you can actually explain the various GAN variations for the inverse problem. Now, in order to understand that one, we go back to the original formulation, classical formulation of parallel least square and its generalization of the stochastic generalization. Now, in the parallel least square is usually formulated in this way. There's a data fidelity term here. This is fold operator. This is unknown is X, and this is Y measurement. Usually, we introduce a Lagrangian term. And now, for a given Y measurement, we try to minimize this cost function to find X here. This is parallel least square. Now here, this problem is for a given Y, you solve this problem every time, okay? Now, in order to actually have an inductive algorithm, rather than solving for the Y and X, for a given one Y to X, we are now think about all the combination of an X and Y. So now your Y and X is now coming from the joint distribution P, Phi, and XY. Now we are trying to find the minimal joint distribution to try to minimize the cost function with respect to all the combinations. Now this is again data fidelity term here. Now, however, we have now introduced a new kinds of regress term here. This is now having a reverse formulation, X and theta relationship with this neural network Y here. But this works as a regression term here. Now here, this is only depending on the X, and this is now depending on X and Y. Why we introduce this regression term? By the way, this is estimating only X, and now we are estimating joint distribution. Now this is actually coming from the geometry, understanding of the geometry for the inverse problem from the optimal transportation point of view here. As I mentioned, this is empirical data for the X distribution, and this is empirical data for the Y distribution. Now, fold mapping is trying to map from here to this measurement based on some kind of fold physics, which is parameter Y5. Now, if we actually transport this one, now we have a new measure, new phi here. The goal is to minimize this one with respect to real measurement Y here. Now, if we just minimize this one, if we want to introduce the regularization, we need to actually impose some kind of constant as well. So the constant we are introducing is there's inverse solution past G theta here. Now this transport this measure from new to new theta here. Now again, we are trying to minimize this and this one together. By adding additional minimization with respect to this, you can actually control the variation of this X domain as well as Y domain. Same thing. This is actually original introduction. However, but you can actually remove the constant in one domain as well, or the other domain. For example, based on these ideas, you can actually think about three variations of optimal transportation problem. Now, for example, you just remove this data fidelity term and just introduce the prior only and the minimizing, try to find the joint distribution. It turns out this is actually related to the GAN or double GAN formulation. We'll talk about that a little bit later. Or if you actually remove the data fidelity term, remove the prior term, and just using the data prior term only, with this is primary formulation. Now, if actually having a dual formulation for this, it turns out this leads to so-called N by N GAN formulation. Now, if you actually use both of them together, it turns out this is actually what we call the optimal transportation driven cycleGAN formulation. Okay, I talk about this one a little bit, one by one. Case one. Now we have a prior term here. Now using this is now Weierstrass measure. So you can actually have a dual formulation from the counteract dual formulation. You have a now counteract potential and this term here. It turns out that this is now discriminator term here, and this is generative term. Usually this was a bar phi C plus, but if you actually constant this function as a one Lipschitz constant, it turns out C transform become minus bar phi here. So that's why you end up with this simple formula under the constant like this. In fact, this is a Weierstrass formulation, and also this is quite often used for the inverse problem as well. Now, for the M-bind formulation, as I mentioned, then you can actually use a data fidelity term here only. Now, if you actually dualize this one from the contracted dual, now you have a bar phi with respect to y and bar phi with respect to x. Now, our goal is to try to find x. This is usually parameterized with respect to neural network. So you are now solving this dual formulation, and that is, in fact, the M-bind formulation. Furthermore, if parameter phi is also distributed with the probability distribution P phi, you can actually integrate with respect to this one again. This is another way to estimate the parameter phi as well. This is M-bind formulation. As you know, as I emphasized, there's no prior term here. This is only measurement, only fitting. Okay. Now, on the other hand, if you actually minimize prior and data fidelity term together, it turns out if you actually find the dual formulation of this, you end up with the cycleGAN formulation. One is a cycle consistent term, and the other is a discriminant term here. Furthermore, if you go to the cycle consistent term and discriminant term, you can actually see the very interesting physics here, dependent term here. Now, the cycle consistent here is now, you have a G zeta here is now coming from the neural network. And F is now coming from the forward physics. Okay? So that means if you sometimes your forward physics is completely known. In that case, this you can just use a complete physics here. If you, in some cases, you know the partial forward physics, like some structures, you can, in that case, you can estimate the parameter for those structures. Or your forward physics is completely unknown. In that case, you need to actually estimate this one using the neural network as well. And now discriminant term is now here in this case is using the Weierstrass formulation, but you can actually use different formulation GANs as well. Okay. Now, based on this kind of understanding, you can actually have a various form of implementation of optimal transport-driven cycleGAN. Original formulation is like this. You have a two neural network, parameter by the theta and gamma here, and the two discriminators here. You're estimating this. There's a four neural network you need to estimate. This is computation expensive. I also need a lot of data. Okay, and also difficult to train, by the way. However, if you know, for example, forward operator is a linear convolution operator, for example, here, convolution operation. Now this problem becomes very simple. You don't need a neural network here. You just estimate the linear layer only here. But still, you need to actually have estimated two discriminators because you need to convert this one using linear. But however, only three generators and three neural networks necessary, and this is simple parameter. So this is much easier to estimate. Okay, much easier to estimate. Now, what if you actually know completely know the forward physics? In that case, this is deterministic for the operation. In that case, you don't need any kinds of discriminator for this part at all. You only need one discriminator and one generator. This is a much simpler problem compared to this problem. So it's much easier to train and you need less data and your result is usually better than this. But however, if you don't know the forward physics at all, you still need to estimate the neural network using another neural network, H gamma here. Okay. Now I'll give you some of the example of this one as well as this one. And this is a standard cycleGAN approaches, but in that case, as I mentioned, we have two different generators here. but I'll introduce how to actually minimize the burden of the training with the two different generators using so-called the switchable cycleGAN architecture our group has developed. Okay, now let's see the unsupervised deconvolution problem from microscopic problem here. Now, as I mentioned, forward physics is coming from this linear deconvolution operation here. And this is a regularization term here from the measurement to X. Now, for this kind of transportation cost, if you find a dual formulation, you end up with this cycleGAN formulation. One is a generator from blurring to clean images coming from here. And forward physics is now using the linear layer with the H corner, which is blurry measurement. Now we have two discriminant and there's cycleGAN system here. Okay. The original paper, we actually applied this on 2D deconvolution problem, but this is the latest work we actually applied this on for the 3D deconvolution problem. In this 3D deconvolution problem of the confocal microscopy stack of the neuron, 3D stack for the cleared brain using the nowadays there are a lot of techniques to clear the brain so that you can actually have a clear brain but still see this kind of GFP marked images, neurons like this. Okay. Now you obtain this one with the 3D stack. Usually, because of 3D scanning has some of the resolution is not good, you usually have a blurry images along the 3D direction, G direction. But usually lateral direction is good. Now, what I'm doing is like this. We are trying to improve the resolution in this X direction using the unmatched data set from this X direction. Okay, so from here, you are now trying to find the neural network G and also 3D convolution kernel F, directly estimating this using the unmatched lateral image and the clean image together. Now, once you train it, now you can see that this blurry image is clearly improved, as you can see in this kind of neural structure. And furthermore, now this is a 2D images. This is a neuron here, blurry version of the XR images. Now you deconvolute it using the neural network. You have much clean images here. Now this is actually the semi-true ground truth images. What you do is we are now rotate the sample so that this is a lateral image, high resolution image corresponding to the XR sections. So you can actually compare versus this one versus this. Still, this computationally, the convoluted image has a very similar architecture. But this is not exactly the same because during the rotation, it's very difficult to find the corresponding section. But still, you can actually see what's going on. Okay. Now, this is an example for the unsupervised learning for the accelerated MRI. In that case, you know the acceleration factor, the downsampling factor. So because of that, forward physics is completely known, so you don't need a discriminator. You just need a generator and one discriminator, and you train in this way. This is a result with comparison result with the supervised learning, and this is the input image at the 4 acceleration factor. And conventional cycleGAN, there is still remaining artifact, Ellison artifact. And proposed method is a very similar compared to supervised learning approaches. And and also in terms of quantity values, is quite similar. Okay. Now, as I mentioned, that if you don't know the physics at all, then you need to actually have another generator. So the question is how to simplify in this case is the standard cycleGAN architecture. In fact, this kind of simplification can be also derived from the optimal transportation problem. Now, this is a well-known formulation for the Gaussian, two Gaussian measure. One is from mu and sigma mu, and the other is nv and sigma v here. If you solve the primary formulation of the optimal transporter, there's a closed-form mapping here. Furthermore, if this is our IID Gaussian, then you have a very interesting transformation from this feature map to here. So now the basic idea is now you are assuming that feature maps follow this Gaussian distribution and try to convert it to another Gaussian measure. In fact, this formulation is basically the same formulation with the adaptive instant normalization in computer vision literatures. In fact, they show that adaptive instant normalization is nothing but the optimal transportation of the feature map from the one IA distribution to another IA distribution. Based on this understanding, we developed a switchable network architecture for the cycleGAN. This is a cycleGAN unit architecture. Now we have a Ardine co-generator. Even though it looks bulky, it's very light network. It's a much smaller, order of magnitude smaller network compared to the unit network. It generates the Ardine code here to the target distributions. Okay. Now you train this network same time as this network architecture. Then what happened? Now this is a switchable cycleGAN architecture, original cycleGAN architecture. Now this is actually one image, one corner image to another corner image, and one dose image to another dose image. Now you have a generator GYX or GXY is a train two network. Now instead of doing this, in this switchable cycleGAN architecture, you have one generator G here. And now we have a different Ardine code, which is trained again. One is actually for the forward direction, and the other is for the backward direction. Now, then by changing the code, you can actually make this one as a forward generator and the backward generator at the same time. Furthermore, one of the nice things about this one is now we have a code here, feature domain code here. Now you can actually interpret in the code domain. That gives also optimal transportation paths between two distributions, as you can see here, from here to here. You interpolate this value, you can actually have an optimal interpolation between the two feature maps. And then you can do a lot of exciting things. By the way, this is at the inference phase. This is during the training phase, but once you train it, interpolation in this feature map, the code is in the inference time at the real-time minute. Then you can do a lot of exciting things. Here, this first application is actually the project we conducted with the Samsung Medicine. What interesting is actually 3D ultrasound image enhancement. Now, usually in the 2D image enhancement, 2D ultrasound probe is just like 1D scanner, a 1D probe, and you are scanning along this direction. This is usually high quality image. But now 3D imaging cases, you have a two-dimensional probe. You can actually estimate the lateral elevation and X-ray image. But usually what happens is, if you actually use a high resolution detector along the 3D, the data is so many, so this is usually much smaller number of resolution compared to here. As you can see, comparison, this resolution is not good with respect to the resolution. Furthermore, this elevation direction is not good resolution either compared to the lateral directions. So our goal is try to improve the 3D ultrasound image quality using the 2D ultrasound image. This is much higher resolution quality, but this is unmatched data. There's no forward operation between the two. So you need actually the two generator cycleGAN, but instead of using the two generator cycleGAN, you actually have a switchable cycleGAN architecture here. Now, once you train it, you can do a lot of exciting things at the inference time. Now here, this alpha parameter, this alpha parameter, is now changing the alpha parameter. You can actually clearly see the difference images here. Now, by inference time, you can actually do this, then you can actually have a different level of the denoising or the image improvement. And you can actually, operator can choose the value depending on their choice. Okay? So this is end of my talk. And in fact, in the part 2 summary is, as I mentioned, optimal transport-driven cycleGAN architecture is more like a stochastic generalization of parallel least square problem. And this is very useful for a lot of inverse problems. And in fact, this kind of geometric understanding by the optimal transport can be actually very useful to generalize this one for other various problems. Okay? With that, I'd like to conclude my talk. Thank you very much for listening.
Yes, thanks a lot for the nice talk. So are there questions? I don't see really signs in Zoom, so just unmute yourself if you have questions. Okay, so maybe I can start with asking. So when you did this 3D deconvolution on the brain images, I'm still a bit confused how you got the training data.
How do you got the 3D data? This is we have actually project going on, national project going on this 3-dimensional microscopy imaging.
Yeah, but you have all this data and they have this deficiency in one direction. And then you say, I mean, they have the lower resolution in one direction, and then you say you rotate by 90 degrees to get training data. Did I get that right? Or what?
No, it's not training data for the 90 degrees. Oh, now let me explain this one here. Now this volume, if you see here, this is actually, if you see this paper, you can clearly see what's going on. Now this volume data, now this along the G direction, usually confocal microscopy resolution along this lateral direction is quite good. However, resolution along in this axial direction is not good. So our goal is try to improve the resolution of this one using the data along this lateral images. This is not matched data, but you can actually easily obtain this one from other direction. And now generator is now try to find the neural network try to find the generator to improve the axial resolution images similar to the lateral resolution images, also unchanged the lateral resolution images as it is. This is based on the neural network. Now this fold measurement is now from these clean images, improved image like this, you are now trying to find the 3-dimensional point spread function such that it actually ends with the original image. With blurring along the G direction. The reason I show you this one is because we don't have any ground truth data, right? Along the X direction. So our collaborators, they actually tried to actually invented a new way, not inventing, they actually have a very nice idea to obtain the semi-pseudo ground truth. So how do they do is, you have this 3D volume and they actually physically rotate the sample.
Okay, and that, okay, then it makes sense.
Yeah, so that's actually, we obtain this kinds of images.
Okay, very good. Thanks a lot. Are there further questions? Okay, so it seems there is nothing urgent, but maybe there is more in the coffee break after. So let me thank you again for the nice talk. I don't know how it goes on this time with the coffee break. Maybe Carola can.
So should I stay in the coffee break or how does it go?
That would be great. So I'm going to carry you with me upstairs.
Okay.
And then I'm sure there will be more questions, discussions. I also have more of a coffee break question, I think.